Hey everyone, this is Abhinav. Welcome back to our series on virtual memory. In this video, we are going to talk about demand paging. Um, in the previous set of videos, we have discussed the more foundational ideas behind virtual memory. What is virtual memory, how it works, how address translation works, how a page table is structured, how a page table works, and the hardware side details, so things like TLB and page fault and all those things we have talked about. So from here on, the next set of topics that we are going to discuss are going to be more interesting because they are strongly correlated to the behaviors of modern day systems. So any system that you either use or operate or build or design, they sort of build on top of uh, these ideas. When you have memory pressure on your system and it starts behaving weirdly and you're trying to investigate, then understanding how things like demand paging work because becomes important. Uh, so, I think from here on you will find these topics much more relevant. So in this video, we're going to talk about demand paging. So we'll start by understanding what is demand paging, why is it needed, and finally, we will end by discussing the internals of the Linux kernel and the internal data structures that make demand paging possible. And understanding the internal data structure is really important here because whenever you're trying to debug virtual memory issues, you have to understand what these data structures are and what they look like because the kernel really exposes them. So any tooling that you use, you should be able to understand uh, all these details to be able to investigate it effectively. Um, so we'll cover that in this video. So let's start by understanding what is demand paging. So demand paging is a very simple idea. So it's lazy allocation of physical memory inside the kernel. So whenever you in your application you're trying to allocate memory. So for example, if you are calling malloc or mmap in your code. So if for example, uh, let's say uh, I could do like for example, I might call mmap um, with some parameters to allocate, let's say. Uh, 4086 bytes, which is one virtual memory page. So if I call mmap like this, uh, the mmap is a system call. It has to go inside the kernel, and we are asking the kernel to allocate 4096 bytes, which is one page. So kernel essentially reserves a virtual memory address range and just gives us back the starting of that address range. So for example, p become uh, might hold the address that the kernel has given us. So 0x, let's say some um, 4 KB aligned value. I'm just using 4096 here, uh, but it has to be a page aligned address anyway. So a map will return us some virtual address. But this address or the page has not yet been mapped to real physical memory. So mmap just simply allocates some virtual address range and it returns immediately. So there is no physical memory allocation at this point of time. So this is the lazy allocation or demand paging. So when exactly the real physical allocation happens? So when you try to access this memory for the first time. So let's say somewhere else down the line, we are trying to do something like this. We are accessing the first byte of this page that we just allocated. At this point of time, what would happen is that first the hardware will try to translate this virtual address to a physical address. So it will try to do that by first checking the TLB. So because this is a freshly allocated address and we have never accessed it, so TLB will not contain the mapping. So TLB will give us a cache miss. When that happens, the hardware has to do a page table walk. So it will go and do a page table walk and try to translate this address. Because this is a freshly allocated address and the kernel is lazy, so it has not yet mapped this address to a physical page. So page table would not contain any mapping. So the hardware will not find any translation in the page table as well. When that happens, the hardware does not know what to do next. So it raises an exception, which in this case is called a page fault. Page fault exception is handled by the kernel. So the kernel has a specific handler, which is, you could think of it like a special routine, which is called by the hardware. So the hardware calls the kernel's page fault handler. It passes the address which caused the page fault, and now the ball is in the kernel's code. So the kernel has to figure out why the page fault happened. If it is possible to handle it safely, then the kernel would handle it. If it was an illegal access, then the kernel will most likely kill the process by sending it a segmentation fault signal. So that is how it works. So on the first call to mmap, the kernel does not allocate physical memory. It resolves a virtual address range and returns back to user space. The real physical memory allocation happens when the first time you access that address, and at that point of time, the page fault happens, and then the kernel will allocate a physical memory for that. And in this case, we just allocated one page, and the first access that we did would have allocated the physical memory for that page. It is also possible that you allocated 10 pages. So instead of 4096 bytes, you allocated 4096 times 10. So 10 virtual memory pages. In that case, every page gets allocated lazily. So, for example, if we just access the first page, only the first page would get a page fault, and that particular page would get a physical page mapping. But the remaining 9 pages would not yet be physically mapped. So they will eventually get mapped one by one as and when we access those pages. So that's how demand paging works. Now the next question is, why do we need demand paging, or why does it exist? Um, so there are, quite a few reasons that we can think of. So one of those reasons is that uh, physical memory allocation is an expensive uh, task. So when you call mmap, so for example, here when we called mmap and we asked for 4096 bytes of memory, if the kernel had to really allocate physical memory at this point of time, it has to do a search. So it has, some sort of an internal data structure where it knows which addresses or which pages, which physical pages are mapped to this process or other processes, and which pages or which address ranges are yet not mapped. So it has to go through that and find the best fit or whatever the algorithm is to find a free physical page and then allocate into your virtual address space and then return. So mmap would become an expensive call. So that is one reason. If the kernel doesn't really have to allocate that physical memory, then mmap becomes really quick. It just returns back. It just gives you, it just checks within your virtual address space which address is not yet mapped. It picks up the right address range, gives it back to you, and it's done. Um, so yeah, so that's one reason that why demand paging exists. Apart from that, there are other reasons as well. So one is that um, the behavior of all the user space applications and systems is also optimized towards demand paging in a way. So, for example, in order to allocate memory, you have to call mmap, and mmap is a system call, and system calls are expensive. So, you don't want to execute system calls too frequently, especially in a hot path. So you try to minimize them. So one way to minimize too many mmap system calls it would be to allocate a large chunk of memory in a single mmap system call, rather than allocating, or rather than calling mmap multiple times. So, for example, if you needed 40 KB of memory, so you would want to do a single mmap call rather than making 10 mmap calls. Uh, so this is the way all real world applications and libraries are written. Even the malloc library behaves the same way, or it is implemented the same way. So it uses mmap under the hood. So it would call mmap to allocate large chunk of memory. It might allocate 1 MB, 2 MB, or 10 MB, some large segment of memory using mmap. And then whenever your application calls malloc, it will find one. For example, if you called malloc for 10 KB of memory, so malloc would find within that large segment where is that 10 KB free block that it can give back to your process, so that malloc doesn't have to go to the operating system every time it needs to allocate memory. So malloc is also doing the same thing. Uh, so the kernel is basically optimizing for this behavior as well. So it knows that uh, malloc may call mmap for a large chunk of memory, but malloc is not going to use all of that memory immediately. So there is no point doing physical memory allocation immediately. So that's why the operating system is also trying to be lazy in that sense. So it is trying to match what uh, malloc and all the real world systems do. So that is another reason. So if operating system was not lazy, then if malloc asked for 10 MB of memory, then the operating system would have to allocate 10 MB of physical memory right at that point of time. So it would have two problems. One is that mmap would become really expensive or slow. Uh, and secondly, if 10 MB was allocated, 10 MB of physical memory was reserved for your process, then any other process now would not, 10 MB is simply gone from the system. Now it is not available for any other process, even if your process is not really using that memory. But demand paging allows that. So demand paging essentially allows multiple processes to be able to execute simultaneously and allocate memory at the same time, even if the amount of physical memory allocated available on the system is limited. So even if you have 1 GB of memory, 1 GB of RAM installed on your hardware, you may still execute several processes simultaneously, and those processes may be allocating a lot of memory. But because the operating system does not have to reserve all of that memory for all the processes at the same time, they can execute without slowing down the system. So the operating system cleverly manages the limited amount of memory by using page reclamation, swapping pages to the disk, swapping unused pages to the disk, and then allocating those physical pages to other process and so on. So in a way, it just works out. But if demand paging did not exist, then this would not be possible. So if two processes simply allocated all the entire physical memory of your system, then the third process could not run at the same time. So basically, those are all the various reasons that is a thing uh, because of which demand paging exists. Um, Now let's move towards how this really works inside the Linux kernel. So I'll be talking about the Linux kernel here because but the ideas are very similar in all operating system kernels. So let's talk about. Let's start by revisiting how the virtual memory address space looks like, and from there we will move towards how the kernel manages this address space. Um, so on x86-64 platform, processor's virtual address space spans from it has this linear virtual address space which goes from the address virtual address 0 up to 2 to the power 48 minus 1. So the virtual address size on x86-64 is 48 bits. So the maximum address range is from 0 to 2 to the power 48 minus 1. This is the address space range. Uh, but not, this is a huge address space. This is like 256 terabytes of uh, memory. But not all of that is actually mapped. So because not most real world systems don't simply have that much of physical memory anyway. So only what certain address ranges are mapped to physical memory, and those are the addresses that you can actually access. So when your process is created, the operating system first allocates memory for uh, certain address ranges in this. So, for example, it may map certain address range for the text section, which is this text section is where your all the executable code is loaded, and it is always towards the lower address ranges. So towards the zero. Not it may not be exactly at zero, but somewhere uh, near to zero. And it goes so depending on how much code your program has. So, for example, if your the amount of executable code is let's say 10 KB, so this text section may go from 0 to let's say 10 times. Let's say 40 KB. If your program has 40 KB of code, then the text section may go from 0 to whatever is uh, 10 times 4096. So, and then this section has some permissions. So all the pages, this is 10 pages, all the pages would have the same permission. So they would be readable and they would be executable.